Hello and good afternoon friends, welcome to CEC-UGC live lecture. Dear friends, in this session today we are going to discuss a very important topic. As you all know that, or you might have heard the term ozone many a times, maybe you have read in newspapers or in books, you might have discussed a lot about it with your teachers. Well friends, today we are going to discuss on this very topic, that is ozone. We would be discussing what ozone is, how it forms, what are its chemical physical properties, and for this we have again with us in our studios Dr. Arun Srivastava. He is Assistant Professor in School of Environmental Sciences, JNU. So I would like to welcome our guest Dr. Arun Srivastava, and I hope that and believe that the way he has delivered the previous lectures, particularly when we talk about the environmental sciences, he has done justification, and today also I hope for the same. So Dr. Srivastava, welcome once again to the EduSet lecture. This word ozone, now we hear this or we have heard this term many a times, but through you, we wish to know what basically ozone is.
Alright, so good afternoon everyone. Today we will discuss on ozone. Ozone we must have heard so many times. Ozone is basically very vital for our life. If ozone wouldn't have been there in the atmosphere, life wouldn't have been possible. But apart from that, ozone is also equally harmful. If the level of ozone exceeds a particular limit, it can be deadly too. It can be destroying for human and other vital lives from the planet Earth. So we will discuss on ozone. What is ozone? Ozone is basically an allotrope of oxygen. It is also known as trioxygen. It is an inorganic molecule. Its chemical formula is OO2. It is written as O3. And one more excellent property of this ozone in comparison to oxygen is that it is very, very less stable than oxygen. It is very easy to break the ozone in comparison to oxygen. Here is the chemical structure of ozone. The intramolecular spacing is around intra-atomic spacing is around 1.278 angstrom, while the angle between two atoms of oxygen in ozone is 116.78 degree. And ozone has double bond between two oxygens, and it is always equilibrium in minus and plus. You can see it in the bottom of the picture shown. As far as physical properties are concerned, its color is pale blue. Its density is 2.144 microgram per cubic centimeter. Its melting point is 192.2 degrees centigrades. Its boiling point is 112 degrees centigrades. While its refractive index is 1.2226. It is soluble in water, not very much soluble, but it is soluble in water, but it is highly soluble in carbon tetrachloride as well as in H2S4 or sulfuric acid. As far as chemical classification is concerned, it is a very dangerous gas. It is supposed to be dangerous. That is why it has been categorized as a hazardous chemical. As far as further physical properties of ozone is concerned, it is a colorless, or as mentioned, it's a slightly bluish color gas. But when it is liquefied, its color is almost blue. It is slightly soluble in water, and at minus 112 degrees centigrade, it condenses to form a dark blue liquid. It is dangerous to allow this liquid to warm to its boiling point, because both concentrated gaseous ozone and liquid ozone has a property that it can easily be detonated or it can be explosive. So it is very dangerous if it is condenses below minus 112 degrees centigrade. At temperature below minus 193.2 degrees centigrade, it can form a violet black color solid. Now, further physical properties. It can easily be detected at a very lower concentration of just 0.01 micromole per mole in air, where it is very specific. It has a very specific sharp order. Somewhat it resembles to the bleach or chlorine bleach. Exposure to 0.1 to 1 micromole per mole produces headache, burning of eyes and irritation to the respiratory passages. Even low concentration of ozone in air are very destructive to organic materials such as latex, plastics, animal lung tissues. Ozone's composition. Ozone in atmosphere is very less. It is just 0.6 ppm of the total gases present in the atmosphere. Or we can say if there is a gas or the total gas is around 1 million liters, so the ozone's contribution will be just 60 milliliter. So, and out of these total ozone, that is 60 milliliter in 1 lakh or 1 million of liter of atmospheric gases, 90% is present at a very high altitude, that is between 20 to 50 kilometers from the surface, and while just 10% is present in the lower level or at the surface level, that is also known as tropospheric ozone. Now, how the ozone is formed? Here is the formation of ozone, how ozone can be formed. What happens when sun rays reacts with the oxygen, or sun rays, what does it do? It breaks down the oxygen into two different oxygen atoms, or we can say the oxygen radicals, and these two oxygen radicals are OO further combines with another oxygen and it forms the ozone. Here again the same picture is there, and especially one more thing I would like to mention, that this sunlight is a very specific part of sunlight is able to break the oxygen, that is ultraviolet rays. So what happens, the ultraviolet rays of sunlight breaks down the oxygen molecule into two different oxygen radicals, that is O dot, O dot, and the wavelength of the light which is capable of breaking oxygen into its two different radical atoms is below 240 nanometers, and this oxygen radical further combines with the oxygen atom to form ozone. Now, what are the chemical properties of ozone? Ozone is a very powerful oxidant. In fact, it is far more oxidizing. It has far more oxidizing capacity than that of oxygen. The high oxidizing potential of ozone may easily cause damage to the mucus and respiratory tissues in animals. It can also damage tissues in plants above concentration of 100 ppb. This makes ozone a potent respiratory hazard and pollutant near ground level. Because of all these characteristics, ozone becomes a pollutant when it is at a surface level. Now, furthermore, in the chemical properties, ozone has a varying half-life depending upon atmospheric conditions, temperature, humidity and air movement. It has a half-life of approximately a day at room temperature. Under certain atmospheric conditions, ozone can have a half-life as short as an hour under atmospheric conditions. Now, as far as oxidizing characteristic is concerned, I mentioned that it is a very big or very powerful oxidizing agent. Except gold, platinum and iridium, it has capacity to oxidize any metal. For example, here I have given the example of copper. It can easily oxidize copper plus to copper plus plus. Now, what are further chemical properties of ozone? It can again easily oxidize nitrogen dioxide into it can easily oxidize nitric oxide to nitrogen dioxide, and further this nitrogen dioxide can be oxidized to further oxides of nitrogen, that is NO3. Ozone can easily react with carbon to form carbon dioxide even at a normal condition, that is room temperature and pressure. Ozone with water can easily oxidize either elemental sulfur or sulfur dioxide to form sulfuric acid. And here is the reaction given. This sulfur easily combines with water and ozone to form H2SO4, and this and apart from the sulfur, it can also combine with sulfur dioxide to form H2SO4. In the gas phase, ozone reacts with hydrogen sulfide to form sulfur dioxide. Now, ozone in the Earth's atmosphere. The standard way to express total ozone levels in the atmosphere is in the terms of Dobson units. Apart from Dobson units, it has other units also. This Dobson units is mainly applied to the stratospheric ozone, or the ozone which is at higher level, that is 20 to 50 kilometers from the surface, while ozone which is present in the surface or near the surface and it is in the form of a pollutant is never expressed in Dobson unit. Rather, it is expressed in micrograms per meter cube or nanomole per mole or parts per billion or parts per million. In fact, the study on ozone, the elaborate study on ozone, were started way back in 1920s. Now, here in this particular picture, you will see how the ozone is concentrated from ground level to the upper part of the atmosphere. Here, the ozone profile is given from surface layer to up to around 35 kilometers from the surface, and you can see between 15 to 30 kilometer ozone's concentration is very high, and here it has reached to around 25 megapascal, and the surface below you can say below 2 kilometer or from surface mean sea level to up to 2 kilometers, its concentration is significant, and further it is very low and keeps on going like that up to around 15 kilometers, and from 15 kilometers where the next layer of atmosphere starts, that is stratosphere, it starts sharply increasing and it reaches to a maximum at around 25 kilometers. Afterwards, it starts decreasing, and around at 35 kilometers, it is more or less at a minimum level. Here, in this particular picture, the ozone's concentration is given globally. You can see this green color, dark green color shows the highest concentration in this particular globe, and the gray color strip, which is around the equator, shows the lowest concentration. So here from this picture we can see the ozone, although the Antarctica's ozone concentration is not provided here, the concentration is maximum as we go towards the pole, whether it is North Pole or the South Pole, but its concentration decreases or it is at minimum level when we are at the equatorial region. Now, as far as ozone's concentration in atmosphere is concerned, it has been divided into different two categories. One is stratospheric ozone, another is tropospheric ozone. We will discuss one by one about these. Now, starting with the ozone's concentration in stratosphere, I think here also very beautifully given the stratospheric concentration of ozone. It is starting from 16 kilometers to up to 48 kilometers, and the contour lines represents the concentration of ozone in Dobson units, and along the x-axis we have the latitude. We can see the maximum concentration again occurs between 24 or around 24 to 30 kilometers, and as we move below it decreases, and as we move further above that it again decreases. So the zone, or we can say at 25 kilometers we have a layer. In fact, it is a very sharp or distinct layer that is known as ozone layer. Now further in stratospheric ozone, this stratospheric ozone is also called as ozone layer. This is mainly between 10 kilometers to up to 50 kilometers, although it is not certain everywhere or throughout the globe. It is highly variable. At poles it is further below, at equator it is at higher elevation. This is also in the units of miles, that is 6 to 31 miles. This layer of ozone concentration are only 2 to 8 parts per billion. So we can say, although we have a ozone layer, distinct ozone layer, but its concentration in comparison to other components of the atmosphere is very low, that is just 2 to 8 ppm, sorry, that is 2 to 8 parts per million. So most of the oxygen there remains in the dioxygen form. Now further in stratospheric ozone in the stratosphere is mostly produced from short wave ultraviolet rays. In fact, ultraviolet rays, sun has a component, different components of its electromagnetic wave, that is ultraviolet rays, infrared rays, visible light, gamma rays, X-rays, microwaves, radar, radio, etc., etc. And the major portion covers are visible, infrared and ultraviolet rays. Out of these ultraviolet rays, out of this entire solar radiation spectrum, ultraviolet rays are responsible for the formation as well as destruction of the ozone. And in fact, it is not that all the ultraviolet rays, its wavelength actually starts at 100 nanometers to up to 350 or 340 nanometers. This entire wavelength is responsible for the formation or destruction of ozone. But a specific wavelength of ultraviolet rays is responsible for the formation of ozone, that is mainly below 240 nanometers. And what happens by ultraviolet rays which is having a wavelength of less than 240 nanometers? What does it do? I think I already showed in the previous slide. What does it do? It actually breaks the oxygen molecule into two different O radicals, and this O radical, in the presence of any third body or any catalyst, any other catalyst, it reacts with the oxygen atom to form ozone. And this ozone again can easily be destroyed with the help of ultraviolet rays, but of different wavelengths. So this formation as well as destruction of ozone is a continuous process taking place at a higher elevation from the Earth's surface, that is in the stratosphere or near the ozone layer. This reaction is basically catalyzed by the presence of certain free radicals such as hydroxyl ions, nitric oxide, atomic chlorine or bromine ions. Now, what is the importance of ozone in the Earth's surface? What is the importance of presence of ozone for the human life on the Earth's surface? Ozone layer actually, what does it do? It actually filters away the ultraviolet rays, which is basically very, very harmful to the human life and other parts of life present on the Earth's surface. And the ultraviolet rays which is mainly being filtered out by ozone layer is about 200 nanometers to up to 315 nanometers. And the peak absorption of ultraviolet rays occurs at a wavelength of around 250 nanometers. And in fact, the wavelength of ultraviolet rays, because I already told that ultraviolet rays wavelength starts from 100 nanometer. So what happens, those wavelengths which are below 200 nanometers to up to 100 nanometers, I mean between 100 nanometers to 200 nanometers, this 100 nanometers to 200 nanometers wavelength is mainly absorbed by either oxygen or nitrogen ion. So we don't have to worry about the wavelength which are less than 200 nanometers. The small unabsorbed part that remains in UVB, in fact I forgot to mention that ultraviolet rays has been categorized into three different categories, UVA, B and C. So a very small portion of UVB radiation is not absorbed, is not completely absorbed by the ozone, but some of it are filtered out to the earth. So what happens, it actually, these are the wavelengths which are responsible for the sunburn in humans, and directly or indirectly it can damage the DNA of living tissues, whether it is plants or animals. UVB at 290 nanometer has a radiation intensity of 350 million times as powerful at the top of the atmosphere as that of the surface. It means that whatever we are receiving at the Earth's surface, the portion of ultraviolet B rays, that is in fact 290 nanometers, is around 350 million times more intense at the top of the atmosphere or at the beginning. So a very, very, very smaller portion of that UVB rays we are finding at the Earth's surface, even though this, although it is very small, but even though it is very, very dangerous to the human life. The same wavelengths are also, and one more part I would like to, one more thing I would like to mention, that although it is harmful, but on the other hand, it is good for the human being, because this wavelength is basically responsible for the formation of vitamin D in the humans. Now again, the ozone layer has a little effect on the longer UV wavelength. It means that wavelength which are more than 350 nanometers to up to 400 nanometers, ozone layer doesn't play any role, or ozone layer doesn't have any active role on these wavelengths. So these wavelengths are usually filtered out to the earth, and in fact it can be responsible for the DNA damage or the sunburn, but not everywhere. It depends upon the immunity of the human or the type of human, and then it can do their effect possibly or not. It is not dangerous to plants as well as to the health of other organisms on the earth. Now here in this particular picture we are showing that how the different components of ultraviolet rays are being filtered out or getting reached to the earth's surface. We will see the band which is in light violet color is of UVC rays. So we can see here that more or less all the UVC rays is either being filtered out by ozone or by oxygen, because this gray line or light green line, it actually represents the concentration of ozone that is along the x-axis, and we can see the UVC rays as soon as it reaches to the maximum portion or maximum concentration of ozone, it is totally filtered out, while UVB rays is partially reaching or in a very small fraction is reaching out to the earth's surface. However, the UVA rays which are having wavelength of more than 315 nanometers or more than 280 nanometers is more or less completely reaching to the earth's surface. Now again, essentially all the UVC rays what I have already mentioned, that is between 100 to 280 nanometers, is blocked by our dioxygen, that is between 100 to 200 nanometers, or by the ozone, that is between 200 to 280 nanometers. The southern portion of this band and even more energetic UV causes the formation of ozone layer. One more thing, how it is being blocked by dioxygen. What does it do? Basically oxygen absorbs those smaller portion of wavelength to dissociate itself. In this way it is utilizing the smaller portion of UVC wavelengths. So, and what happens, this oxygen atom in terms are responsible for the formation of ozone. When a single oxygen atom produced by UV photolysis of oxygen below 240 nanometers react with more dioxygen, the ozone layer itself then blocks most but not quite all sun-burning UVB, which is between 280 to 350 nanometers. The band of UV closest to visible light, that is between 315 to 400 nanometer, is hardly affected by ozone, and mostly it reaches to the earth's surface. Now there is one more important point, that is ozone layer depletion, or in general we call it as ozone depletion. What is ozone depletion? Ozone depletion, basically it can be described as two distinct but related phenomena observed since the late 1970s. A steady decline. What is this? Actually it is a steady decline of about 4% per decade in the total volume of ozone in the Earth's ozone layer. Also a much larger springtime decrease in stratospheric ozone over Earth's polar regions. The latter phenomenon is referred as ozone hole. Apart from this, there is a well-known stratospheric phenomenon that is called as springtime polar tropospheric ozone depletion event. So in fact there are three different types of ozone depletion. One is the total ozone depletion across the globe. Another is ozone depletion around the poles, northern and southern, but during springtime only. Apart from that, there is again a springtime polar depletion of ozone layer, but ozone concentration, but not in stratosphere but in the troposphere. Here in this particular picture, it has beautifully been shown how the hole is formed. Especially you can see that this light blue color represents the diminishing concentration or lowering concentration of ozone, especially in the southern polar region, or more or less the entire Antarctica is diminishing or is lacking of ozone. In this particular picture also, a decreasing pattern of ozone is shown from 1980 to around 2000. We can see here there is a significant decline in the ozone's concentration 1995 onwards. Again, this picture also we will see that this, in fact, it has been monitored at two different places. We can see that there is a sharp decline in the ozone's concentration from 1990 onwards, and again there is a peak of ozone around 2002 or 3, but again there is a sharp decline. But after 2010, the trend of ozone is increasing, or the concentration of ozone is slowly increasing, and it is basically because of the phasing out of the ozone depleting substances. And coming back to the same section of ozone depletion, the details of polar ozone hole formation differ from that of mid-latitude thinning. This thinning is caused by the catalytic destruction of ozone by atomic halogens, and the main sources of these halogen atoms in the stratosphere is due to photodissociation of man-made halocarbons, refrigerants, solvents, propellants, etc. They are basically CFC, that is chlorofluorocarbons, SCFCs, that is hydrochlorofluorocarbons, freons, or halogens. These compounds are transported into the stratosphere after being emitted at the surface. Both types of ozone depletion have been observed to increase as emission of halocarbons increases. CFCs and other contributory substances are referred to as ozone depleting substances, or ODS, since the ozone layer prevents most harmful UVB wavelength, that is 280 to 350 nanometer of ultraviolet light, from passing through the Earth's atmosphere. It is suspected, or it is found, that a variety of biological consequences such as increasing skin cancer, cataracts, damage to the plants, and reduction of planktonic population in the ocean's photic zone may result from the increased UV exposure due to ozone depletion. Thus, observed and projected decrease in ozone have generated worldwide concern, leading to adoption of Montreal Protocol that bans the production of CFC, halogens, and other ozone depleting chemicals such as carbon tetrachloride and trichloromethane. Now, something about Montreal Protocol. What is Montreal Protocol? Montreal Protocol, actually it is a protocol on substances that deplete the ozone layer. It is basically an international treaty designed to protect the ozone layer by phasing out the production of numerous substances that are responsible for ozone depletion. It was agreed on September 16, 1987 and entered into force on January 1st, 1989, followed by its first meeting in Helsinki in May 1989. Since then, it has undergone 8 major revisions. Now, I think this is it about the stratospheric ozone. Now, something about tropospheric ozone. Tropospheric ozone is, although in a very, very less concentration, but it is very significant as far as health and other issues are concerned. And in fact, it is an atmospheric pollutant. It is basically formed by the reaction of hydrocarbons and nitrogen dioxides in the presence of sunlight. Ozone in turn can form hydroxyl radicals, that is HO, and this HO radical can form peroxyethyl nitrate, that is also known as PAN. This ozone and PAN are the major components of smog, and in fact smog is considered to be a very dangerous or very important air pollutant. The atmospheric lifetime of tropospheric ozone is much more than that of stratospheric ozone. So in fact it is 22 days, while we discussed that the atmospheric lifetime of stratospheric ozone was either 1 day, sometimes it was 1 day, or even further less, that is around 1 hour or so. But here it is significantly more, that is 22 days. The reason behind that is because ultraviolet rays are very active in the troposphere, so it can easily break or dissociate the ozone to form oxygen, but here the availability of ultraviolet rays are very less, so their dissociation is not possible. So whatever the mechanism, other mechanisms by its reaction with the other hydroxyl radicals, etc., these are the methods by which it can be destroyed or diminished. So in fact, apart from that, apart from its reaction to the hydroxyl radical for its removal, the another removal mechanism is that it can also be deposited to the ground level. Now, what could be the impacts of ozone on different components of our Earth system? We will start first with agriculture. In fact, it can significantly reduce or affect the agriculture, and because the increased ground level ozone can easily interfere with the photosynthesis process, and once the photosynthesis process is affected, it can lower down the yields. Now, apart from agriculture, it has also very strong effect on polymers. Basically, it can easily crack the polymers. What it does actually, ozone can easily destroy any polymer which possesses double band with its chain structure, such as natural rubber, etc. And in fact, these products made using these polymers are especially susceptible to attack, which causes cracks to grow longer and deeper in due course of time. Here in this picture, it is shown that how a rubber tire is being cracked by ozone. Now, apart from these things, ozone is also considered to be a significant greenhouse gas. Although ozone was present at ground level much before the industrial era, but it has been found that its concentration has significantly been increased, whether it is peak value or the background value after the industrial era. Ozone in fact acts as a greenhouse gas because it can easily absorb the infrared energy which are being emitted from the Earth's surface. Quantification of its greenhouse potency is very difficult because it is not present uniformly across the globe. However, it has been a comparative statement is given in comparison to the carbon dioxide. The annual global warming potential of tropospheric ozone is between 918 to around 1022 tons carbon dioxide equivalents per ton tropospheric ozone. This means that on per molecular basis, ozone in the troposphere has a radiative forcing effect roughly 1000 times as stronger as CO2. However, tropospheric ozone is a short-lived greenhouse gas which decays in the atmosphere much more quicker than that of CO2. This means that over a 20 years of time span, the global warming potency of tropospheric ozone is much less, roughly 60 to 69 times CO2 equivalent. Initially, it was around 1000 tons CO2 equivalent, but because of its short-lived lifespan, it has decreased to 60 to 69 tons CO2 equivalent per tons of tropospheric ozone. Because of its short-lived nature, tropospheric ozone does not have a strong global effect, but has very strong radiative forcing effect on the regional scale. In fact, there are regions of the world where tropospheric ozone has a radiative forcing of up to 150% than that of CO2. However, on an average, it has just 25% than that of CO2. Now, what are the health effects of ozone air pollution? There is a great deal of evidence to show that ground level ozone can harm lung function and irritate the respiratory system. It is in fact a very significant air pollutant, I must mention. Exposure to ozone and the pollutants that produces, it is linked to premature death, asthma, bronchitis, heart attacks, and other cardiopulmonary problems. Long-term exposure to ozone has been shown to increase risk of death from respiratory illness. In a study, 4,50,000 people of United States in different cities showed a significant correlation between ozone level and respiratory illness over the age of 18 years. The study revealed that people living in cities with high ozone levels such as Houston or Los Angeles had an over 30% increased risk of dying from lungs diseases. In India, we have prescribed limit by Central Pollution Control Board. It is 100 micrograms per meter cube on an 8 hours average and 180 micrograms per hour on 1 hour average basis. However, it is been found by various scientists that even a concentration of just 100 microgram per meter cube can be fatal or can be lethal to those who are susceptible or have some history of respiratory problems. Ozone concentration is in fact generally measured on 8 hours basis. Targets should, and it is also said that whatever I have mentioned, that 8 hours basis it should be 100 micrograms per meter cube, but it is not that this condition should prevail throughout the year or 365 days, but it should be just for 25 days in a calendar year. Now, what are the other impacts of ozone? Apart from these mentioned impacts, one more thing I would like to mention, that when ozone, when heat waves are there, ozone's concentration rises, and because during heat waves, the plants which are a big absorber or big reducer of ozone, their activity becomes less, and so the less consumption of ozone occurs. Because of this reason, ozone concentration is elevated during the summer, especially during the heat wave periods. In India, it is also known as low period. Now, apart from this, it has significant impact upon the physiology of human being or other organisms. Ozone, along with reactive forms of oxygen such as superoxide, single oxygen, hydrogen peroxide and hypochlorite ions, is naturally produced by white blood cells and other biological systems, as means, and here it is vital for us because it is produced inside our body by white blood cells to destroy the foreign bodies or unwanted bodies. But when ozone and one more thing, ozone has a strong characteristic to react with double bonds of organic compounds, and because of this reason it is very fatal for human body. When ozone breaks down to dioxygen, it gives rise to oxygen free radicals which are highly reactive and capable of damaging many organic molecules present in our body. It is also believed that powerful oxidizing properties of ozone may be contributing factors for inflammation in humans. When ozone is inhaled, what does it do? It actually reacts with the compound lining of the lungs to form specific cholesterol derived metabolites that may ultimately cause heart diseases. Due to strong oxidizing properties, ozone is a primary irritant affecting especially the eyes, respiratory systems, and it can be hazardous even at a very, very low concentration. Ozone has also been linked to adverse effects on the plant growth. Ozone can reduce the chlorophyll and various other vital parameters required for the growth of plant, suppressing the yields of plant. Here in this particular picture, it is shown that how ozone at ground level has affected the leaf of a plant. This is known as this special kind of disease known as red elder leaf, and here you can see the red spots present on the leaf surface is caused by ozone pollution from the surface. Now, some positive points of, apart from these, some positive points of ozone. Ozone has got huge, so many applications, and because it is a major disinfectant and thereby it is used in laundry, whether for hospitals or food factories or care homes, etc. It is also used as disinfectant in water in place of chlorine, because chlorine when it exceeds certain amount it becomes a pollutant. So in place of chlorine it is used in water to disinfect. Apart from that, it is also used to deodorize air objects, such as in buildings or in places where the fires have just occurred. So to overcome that odor, it is used. Apart from all this, it is also used to kill the bacteria on food or on contact surfaces. It is also used to sanitize the swimming pools, spas, and stored grains, or where the grains are stored. It is also scrub yeast and mold spores from the air in food processing plants. It can also be used to wash fresh fruits and vegetables to kill yeast, molds, and bacteria. It can chemically attack contaminants in water like iron, arsenic, hydrogen, sulfide, nitrates, and other complex organic compounds. What does it do actually? It attacks chemically to these ions or these metals and forms a flocculent, and this flocculent can easily grow in size and can easily be filtered out or removed from the water body. Apart from these, it is also used to manufacture chemicals compounds via chemical synthesis. It can clean and bleach fabrics. It can also assist in processing plastic to allow adhesions to the inks. It can also be used to check the age of rubber, because once it is exposed, ozone, that rubber is exposed by ozone, and with the help of that we can estimate how long a rubber can survive or sustain. Now, what are the methods to produce ozone? There are many methods, but here we have mentioned just 4 different types of methods for the formation of ozone. Number 1 is coronal discharge method. In this method, in fact this is the most common method for the ozone generation. What does it do? Actually, with the help of coronal discharge tube, we can produce ozone of medical or industrial grade. Apart from this, ultraviolet lights are also utilized for the formation of ozone. They are basically known as UV ozone generators or vacuum ultraviolet ozone generators. And in this, actually it implies a light source that generates a narrow band of ultraviolet rays, and that uses the same technique what happens in the stratosphere, that it breaks down the oxygen molecule, and further one oxygen molecule, broken oxygen molecule, combines with the oxygen atom to form ozone. Apart from that, another method is cold plasma. In the cold plasma method, pure oxygen gas is exposed to plasma created by dielectric barrier discharge. The diatomic oxygen is split into single atoms, which then recombine in triplets to form ozone. The next one is electrolytic method, and in electrolytic ozone generation, what does it do? It actually splits water molecule into hydrogen, oxygen, and ozone. In most electrolytic ozone generator methods, the hydrogen gas will be removed to leave oxygen and ozone, so we are left with oxygen and ozone, and from there ozone can easily be removed out for utilizations.
With this note, thank you, sir. Thank you so very much. Again, you have given a very fruitful session to us, because with the help of this session, we are able to understand more about the ozone, as you explained about the various properties as well as the impact of ozone, as well as how it can be used, that is the various applications of the ozone. If we talk about the ozone, or basically the composition of ozone, or we signify ozone, we used to say O3. So what this O3 is, if we try to explain it?
O3 is basically allotrope. Allotrope is the hard form of any element. There are many allotropes. Like carbon has many allotropes. I can make you understand in this by this method. Like diamond, graphite, these are carbon. Carbon is a gas, but diamond is also carbon, having the same chemical composition of carbon, but is very strong. I mean, diamond can be considered as the hardest material present. So the same carbon on the one hand is in the gaseous form, on the other hand is a very hard material. So and apart from these, there is one allotrope of carbon, that is graphite. Graphite is very, I mean, it can easily be broken, so it is somewhere between diamond form of carbon and elemental form of carbon. So this here, the carbon has, in fact, apart from this, carbon has so many other allotropes also, but I just discussed 3 different allotropes. Similarly, oxygen has some allotropes, and one among them is this ozone, and this ozone is basically 3 atoms of oxygen. Like oxygen is 2 atoms of oxygen, and here it is 3 atoms of oxygen has been combined to form the ozone molecule. And in fact, ozone molecule is not as strong as the oxygen molecule.
Okay, this is the way you have described the allotropes as you described yourself. Now the question arises, as we have many times heard about the ultraviolet radiations. Does these ultraviolet radiations has any effect on the ozone, or is there any connection between the ozone and ultraviolet radiations?
In fact, the ozone formation and ozone destruction both are caused by the ultraviolet rays. Ultraviolet rays are the parts of electromagnetic radiation which is coming from the earth. So what does it do? In fact, ultraviolet rays has a extended wavelength. It starts at a wavelength of 100 nanometers, and it can be up to around 400 nanometers. So this 300s gap has a very vital role to play, whether it is the formation of ozone or the destruction of ozone is concerned. Keeping these into mind, the ultraviolet rays have also been divided into 3 different categories, that is UVA, UVB, UVC. So the lowest part is UVC, the middle part is UVB, the longest part, or the part which has longer wavelength, is UVA. So what does it do? The shortest wavelength, that is in the category of UVC, has high energy level. I mean, its energy carrying capacity and its penetration power is far more than that of the other 2 wavelengths of ultraviolet rays. So with this high energy level, it can easily break down the oxygen atom, oxygen molecule into its atomic components, that is O and O. And this O and O, one of the O again combines with the oxygen atom, that is O2, to form O3. In this way, ultraviolet rays is being utilized for the formation of ozone. On the other hand, the same ozone, the same ultraviolet rays, but of different wavelength. What does it do? It again attacks or penetrates that ozone atom to dissociate it into its further components, that is oxygen and O radical. So in this way, ultraviolet rays play a very vital role in the formation as well as in the destruction of ozone molecules.
Now, as per the, if we talk about the ozone, as you have explained that there are, and we know that there are different layers of layers in the atmosphere. So, where does this ozone exist? In which layer of the atmosphere?
In fact, our atmosphere has been divided into 4-5 different layers. That is, the lowest one is troposphere, where we live, and above that is stratosphere. If we fly somewhere, sometimes the planes fly at the boundary of stratosphere and troposphere, or at the junction. So in this way, sometimes we are there in the stratosphere also, and above that stratosphere is troposphere, stratosphere, afterwards is mesosphere, then it is exosphere, and then the final one is ionosphere. So the troposphere, the lowest part or the lowest layer, is from surface layer of the earth to up to 20 kilometers, and somewhere it is 15 kilometers also. So it varies between from surface to 15 to 20 kilometers, and from 15 kilometers the other layer, that is stratosphere starts, and it can go up to 50 kilometers. This ozone layer actually starts, or the layer or the maximum concentration of ozone is found at the junction of that troposphere, stratosphere, or at the boundary of these two layers, and from there it starts and it can go up to 50 kilometers. Sometimes we can say that this ozone layer, in fact ozone layer is not smooth or uniform throughout the globe, but it is present everywhere throughout the globe, but in varying thicknesses. So this ozone layer is present between, we can say, between 20 to around 50 kilometers from the Earth's surface. However, the concentration of ozone is found from the Earth's surface, or the presence of ozone can be found or can be noticed from the Earth's surface to up to 50 kilometers.
Now the question arises, as we discussed about the various health issues because of the ozone. Now again my question is, as I used to ask you many times, does this ozone layer or the ozone has ill effects on the skin or the cancer diseases can
Yes,
grow because of the ozone?
very dangerous. In fact, it is dangerous to human beings as well as it is dangerous to the crops, as I mentioned in my presentation. The major diseases that can be caused by ozone are the first and the noticeable diseases is skin cancer, because once it is because of the lack of ozone, not due to the presence of ozone. If you are asking because of the ozone, then I'll say that because of the ozone, the major diseases can be caused or related to the respiratory system, whether it is lungs diseases or respiratory illnesses. It could be short term as well as long term. In fact, I said, or in fact I mentioned in the presentation also, that even a very small quantity of ozone are lethal or noticeable. So what happens, even a very small quantity of ozone is present, the first symptom is that it can start irritating our eyes. Apart from that, it can start irritating our respiratory valves as well. So this is the first symptom, but it is a very short-lived. Once we are away from that portion, or we are gone away from the ozone where the ozone is present, these problems disappear. But if we are living there, or we are in a place where this ozone is present continuously and we are bound to inhale this ozone, so it is possible that in due course of time it can cause some long-term or irreversible diseases, and those diseases are very harmful. It can be bronchitis, asthma, as well as in some cases it has also been linked with the lungs cancers.
As with the help of your slides, you had shown a picture, and as you described about the polymers, how polymers are not exactly they are destructed, but the ill effects could be seen on the polymers also. So can we say that all the products made of the rubber basically could be affected because of the ozone?
Yes, ozone has, depends upon how much ozone it is being exposed to. Definitely ozone can have ill effect on the rubbers or polymers, but we can protect it. There are many mechanisms with the help of which it can be protected. And what do we do to protect those rubber or polymers? A polythene layering is done. That is why in tires, etc., whatever we use, it comes with the polythene coating, and that is, in fact, it is also to protect it from moisture, but apart from that, it also helps the rubber to fight against the ozone.
As you explained more and more about the ozone, its impact, you have explained us the health issues it caused, you have explained in this particular lecture. So what is the difference between ozone and ozone layer? Is there any?
Yes, there is. Ozone, I told in the beginning only that ozone is vital for us. If ozone wouldn't have been there in the atmosphere, life wouldn't have been possible on the Earth system. So ozone is in fact life giver, as well as it can snatch the life too. So in fact, what is the vital thing about ozone is that I mentioned that ozone layer is present there. So whatever the ultraviolet rays which comes from the sun is shielded or is prevented by that ozone layer, or it bars those ultraviolet rays to reach the Earth's surface, because once it reaches to the Earth's surface, it might have many significant impact upon human life as well as the crop pattern. The major concern or major problem that it can cause is skin cancer or other skin diseases which can be caused by the presence of ultraviolet rays. Apart from that, it can also have very ill effect upon the crop pattern. So thus we can say the ozone layer is vital or very important to us. In fact, recently because of the uses of various refrigerants or the gases which is used in air conditioned and refrigerators, this ozone were getting destroyed, and due to this region this ozone holes were occurring and the ultraviolet rays were started reaching to the Earth's surface, and many incidences of such
well explained, sir, well explained. Many of the cases have emerged out, but it's time to say goodbye to you because we are winding up this lecture, and I hope that in future lectures also we would be learning more on the environmental sciences. Thank you, sir. Thank you, sir.